So in this video we're going to keep talking about the E2 reaction, and in particular we're going to talk about the direction of elimination. So how do we know which hydrogen eliminates if there's more than one adjacent hydrogen to that electrophilic carbon that we are doing the elimination from? So one thing we have to consider is what is the regiochemistry of the reaction? Which stereochemical product dominates when there are two or more structural isomers that can be produced? So something we have to think about now is something called Zaitsev's rule, which is essentially as follows. The major alkene product is the one with more alkyl groups on the carbons of the double bond. So when we think about which product is the major one, we have to consider Zaitsev's rule now. So for example, with this reaction down below, we can see that we have two adjacent carbons to choose from with hydrogens to do our E2 elimination. And the question becomes, where does the alkene form? Right, as we just discussed, based on Zaitsev's rule, the major alkene is the one that's more substituted. So for example, looking at our hydrogens here and looking at our base, the major product should be the more substituted alkene. So based on that, we see that the major alkene product is the one that is more substituted. In this case, it's di-substituted, right? We have two methyl groups on this double bond. And likewise, I'll do this in a different color to show the different reaction happening. If we were to choose from the other side, the less substituted side, you would see a different product. In this case, it would be less substituted, right? This is just mono-substituted. We only have one ethyl group coming off that double bond. So we would say this is the minor product, and the di-substituted alkene is the major product, right? And this causes a general trend where the more substituted alkene is lower in transition state energy and has a more stable product, right? As we can see here, right, with R being just any group, any number of carbons, we have the mono-substituted product way at the end here, right, less stable, and then the tetra-substituted product at the right end, and that is the most stable product. And we can see, right, mono-substituted is less stable than di-substituted, and we have, right, three different options for di-substituted. We have the Z isomer, E isomer, or achiral, where both substituents are on the same carbon, right, and our hydrogens make this a achiral molecule. And we have tri-substituted and finally tetra-substituted. And you can think of it like this. You can almost think about the alkene as being a reactive site, right? And the more carbons are on that double bond, you can think of it being more protected, quote unquote, right? Meaning it's more stable, right? Less reactive. So now that we've learned Zaitsev's rule, we of course have to look at some exceptions. So the first exception we'll look at is something called a Hoffman elimination. And it will have always this general sort of look where there's an elimination by a molecule with a quaternary nitrogen, right? Nitrogen with 1, 2, 3, 4 carbons, right? And this nitrogen here is the leaving group, okay? And I'll show you an example of this. It probably looks kind of weird right now. But essentially, right, based on what we just learned with Zaitsev's rule, you would think you would eliminate this way, right, to form a double bond between these two carbons. However, we actually go to the less substituted side when we're doing this reaction. So let's see what that looks like. Again, we do that sort of 180 backside attack when we're forming the double bond. And now we have our less substituted alkene, and the leaving group, right, is just the nitrogen now with that lone pair on it. And then, of course, water from our hydroxide ion that got neutralized, and both sides of the reaction are balanced, right, with temperature here just sort of saying that this promotes, right, an elimination reaction. So we can see, right, the alkene is mono-substituted, but the Hoffman elimination prefers that. And the reason why that this happens is due to sterics, right? The 3-methyl groups on this nitrogen are rather large. And one way we can sort of take a closer look at this is by a Newman projection. So I didn't have it drawn here, but let's pretend that this leaving group is on a wedge, okay? Because this is a chiral carbon, right? We have 2 different groups on the side here, a hydrogen, and then this quaternary nitrogen. So let's say this is on a wedge. So if we were to look down, right, this carbon to this carbon, the Newman projection would look like this, right, where we have that ethyl group kind of pointing up here. And we have our 2 hydrogens down below. And then the nitrogen, right, will be on the right side here, right, because it's wedged. It is pointing towards us when we're making our Newman projection. And of course we have a hydrogen on the dash position. And then we have CH3, right, down below. And so we can see, in order to do that elimination reaction, right, on this side, it would have to come from this hydrogen, right, because this hydrogen is 180 from that quaternary nitrogen. However, we can see here that there is this gauche interaction, right, between the 2 biggest groups in the Newman projection, this ethyl group and this quaternary nitrogen, right. This is a less stable transition state, right, for that elimination to occur. However, if we were to look at the other site for the elimination reaction, and I'll draw this one in red, so we're looking down this carbon to this carbon, we can see that we actually have a much more stable elimination for the transition state. Right, so we're looking at this bond, so now this nitrogen will be on the left side here. Hydrogen on the dash. And we have CH2, CH2, CH3 as our group down here. And now the hydrogen for elimination is right here, right 180 degrees apart from that quaternary nitrogen, and there's no gauche interaction anymore, right? There's no large group sort of hindering that space. So we can see that this is the more stable transition state for the elimination reaction. Okay, and this is kind of where Newman projections come in handy for looking at the 180 degree dihedral angle between the eliminating hydrogen and the leaving group. And this will really help to dictate what alkene is forming. Okay, so again, in short, for the Hoffman product, the elimination that occurs is the one that gives the major alkene with fewer alkyl groups, right? So it's directly opposite to Zaitsev's rule. The other exception to Zaitsev's rule that we'll talk about is when we have conjugation to a newly formed double bond, meaning, right, just the most amount of double bonds adjacent to each other, which we know from all these examples I've given is good for resonance, right? So looking at this molecule here, we might think, okay, if we're following Zaitsev's rule, we would have the double bond here, right, because this would be a tri-substituted alkene, but we would actually rather have it in this position to give us a conjugated product. So what does that look like here? And we have our bulky base, which we know is good for E2 eliminations and not SN2 eliminations. And so we would take that hydrogen, and we'd kick off that bromine here, and we would now have our more conjugated alkene. Right, more conjugated. And our major product. In general, for reaction questions, I'll ask what's the major product, but sometimes maybe I'll also ask what is the minor product. So if I was to ask for the minor product, right, it would look like this, with our product not conjugated. So this would be our minor product. So these are the two major examples for an exception to the Zaitsev's rule, right? Conjugation and the Hofmann elimination, which always has a quaternary nitrogen, right? That positively charged nitrogen, which makes for, by the way, an amazing leaving group because we're going from a positively charged nitrogen to something that's neutral, okay? So that makes for an amazing leaving group. But in general, right, with Zaitsev's rule, we're pretty much always going to follow this for elimination reactions, where the more substituted alkene is the one that forms. So just be on the lookout for these exceptions, okay? The Hofmann elimination and conjugation to previously existing double bonds. So in lecture, what we'll do is we'll go over some examples of the different things we've talked about, where we'll go over the major and minor products of the following reactions.